Got it. My name is Denis Pierrot, so I work at NOAA AOML in Miami, Florida. I lead this effort called the pCO2 effort, where we install these instruments that I'm going to be talking about, the General Oceanics pCO2 system on board ships. And I'll talk a little bit about our program quickly. So let's go to the next slide, please. All right, I see it on my phone, but not on the computer. Great. All right. Okay, I'm going to be working off my phone then. The first thing I want to do, and that was one of the questions from somebody who said, tell us why we're doing these measurements. So the reason why we're doing these measurements is because the carbon dioxide that we release in the atmosphere has a lot of consequences on the climate and on the ocean health as well. As you know, it traps radiation in the atmosphere and warms up the atmosphere, which has a whole series of consequences from ice melting, which creates changes the ocean circulation, which is, as you know, probably very important for the climate. It also creates sea level rise. In the ocean, the carbon dioxide is an acid, and so we're discovering now that it acidifies the seawater, which are also a lot of consequences for the food chain, and the what's called the animals that live while creating a calcium carbonate shell. Their capacity of creating that shell is affected by the acidity of the ocean. So it has a whole sort of consequences. So basically, the carbon dioxide that releases in the atmosphere has a lot of influence effects. I mean, on the climate and the food chain that we depend on, and that this is why it's very important to understand what's happening to this carbon dioxide. Next, please. The carbon cycle. This is a quick slide about what's happening. So we release the carbon dioxide in the atmosphere, as you know, and this carbon dioxide has basically two pathways. It can go back to the land through photosynthesis. Basically, that's about a quarter of what we release goes back in the land, and another quarter of it goes into the ocean. So the ocean, and of course, the rest stays in the atmosphere, and this is why we see a gradual increase of the concentration in the atmosphere since the Industrial Revolution. So the ocean creates a great service to us by absorbing about a quarter of the carbon dioxide that we produce in the ocean. Next slide, please. All right. Once in the ocean, right, so it equilibrates with the surface. Okay. And once it's in the ocean, you've got two ways. It's what's something we call the physical pump, which is so it gets entrained by currents and other mechanisms. It could interact with ions in the ocean to create like calcium carbonate, for example, and precipitate out of the solution and go down to the deep. It also, as you know, like on land, there's photosynthetic organisms in the ocean, like phytoplankton, that absorb the CO2. There's also respiration that creates CO2. So it's a whole mechanism that we call the biological pump. These organisms breathe and absorb CO2, and then they die, and then their organic matter sinks to the ocean. And so this is what we call the biological pump. This is two pathways of the atmospheric CO2 in the ocean. All right, so next slide, please. Okay, I'll update here. All right, so out of these pumps, you add on the circulation of the ocean. You got vertical mixing by all kinds of processes. There's internal recycling, horizontal, vertical transport, upwelling, and then you have the surface transport as well. That one we call the Great Conveyor Belt. That circulates the seawater surface and brings it out to deep and so forth, and resurfaces other places. So it's a complex series of mixing, and so you take the the absorption of CO2 by the ocean mixed with these phenomenon and these currents, and then you get a picture like the one on the next slide. If you could show that, you will see, there we go, a map then of the distribution of CO2, on the ocean. You see certain areas of the globe in yellow and red, for example, have carbon concentration higher than the atmosphere, and the blue areas, which is usually the mid-latitudes, have lower concentration. And these, these patterns basically change also with time and with season. So it's a complex, system that we are trying to understand. These areas in yellow and red, which have higher concentration of carbon than the atmosphere, that the CO2 in these regions come out of the ocean in the atmosphere. And the blue regions, the CO2 tends to go inside. So, and as I said, it's changing. So this is what we're trying to do with our measurements, is map the concentration of CO2 throughout the globe as much as possible, right? And with auxiliary measurements of currents, of pressure, temperature, salinity, trying to understand this system and model it so we can hopefully, predict what's going to happen to the CO2 that we put in the atmosphere. Next slide, please. So there's different ways that we can measure the CO2 at the surface of the ocean. We have buoys like this MAP CO2 system, moored autonomous pCO2 system. There's a whole series of array like in the Equatorial Pacific, and there's some in the Atlantic. We are kind of starting to put those on autonomous surface vehicles like gliders, and the latest ones, which are sail drones, the little red sailboat on there, which is kind of the new toy for kind of measurements. But and this is not what the SOUP CO2 group does. So what we do is we use ships of opportunity, right? So next slide, please. Our program, yes, uses so all kinds of ships. We have research vessels, we have cruise ships, and we have cargo vessels as well, even though the number of cargo vessels is diminishing because these installations are very problematic. But you can see that our program here, the number of ships varies depending on the year, but on average, we have about right now 15 ships and increasing, collecting data. And we produce we used to produce about 500,000 data points per year. And we're really trying to increase that number because it's not sufficient. You see the distribution of data on the map from year to year, and you see a lot of gaps in there. So we're trying to fill those gaps as much as possible. Next slide, please. All right, so we're increasing our program. We're starting to create what we call the SOCONET, which is an integrated network that would do these measurements. Right now, we are just a group of 5 partners. We each have our instrumentation pretty much, even though we're trying to unify this, but we have our own ships and we have our own interaction with ships and our own ways of processing the data and submitting it pretty much. And so we would like to create this network where everything is a little more integrated and centralized, and increase the conformity in instrumentation, data transfer protocols, data processing, and so forth, which would greatly increase the number, not only the number of data, but also the quality of the data and in uniformity. So this is what we're trying to achieve right now. So next slide, please. All right, so this is the instrument that I'm going to talk about. Some of you have used other instruments, and we can discuss them a little bit later. But this is the instrument that we're trying to really use throughout all the installation. We believe this is the best instrument to do what we want to do. This is called it's built by General Oceanics right now, but this is really an instrument that was built by the community of scientists. We got together and designed a system that we think is the best to be mostly autonomous and run month at a time with some bells and whistles to prevent issues. So we transferred the technology to General Oceanics, who's building them now. And so General Oceanics we call GEO, and so we call this the GEO system. It's composed of basically two boxes. One we call the wet box, and the other one is dry box for obvious reason. The wet box has the water circling through it. And we have a set of standards that we use to calibrate the analyzer. So I was going to first point out to the main parts of this system, which you need to know. So on the dry box, which is on the right, with the main part of this with computer power supplies, but the LICOR analyzer is the analyzer that will measure the carbon concentration in the air that flows through it. We can measure, the CO2 in the water or in the atmospheric air as well. And we use standards to calibrate the analyzer. So we have this multi-position valve that allows you to select which gas you want to analyze, right? So this is in the dry box, and on the wet box, then you have the main part is the equilibrator. Yes, on the left side there. So it's labeled. This is where the equilibration of CO2 between the water and the air above it occurs. So the principle of this is that if the air above this water has the same concentration, or is at equilibrium, I should say, with the water, then we measure this gas through the analyzer and we can back calculate the concentration in the water. Okay, so this is the principle of it. So we take this what's called the headspace gas, which is the gas above the water in the equilibrator, and we circulate it. We try to dry it as much as possible because water vapor in the gas is an interference for the measurements. So we have two mechanisms that we dry the gas with. The first one is the chiller, which we also call the condenser, because it basically cools the gas and condensate the water vapor out of the gas as much as possible. And then we have some little white aqueduct filters to prevent liquid water from going any further. But the Nafion tubes also dry the gas further by extracting the water vapor through a membrane out of these Nafion tubes. And then it's circulated through the analyzer. And of course, this circulation occurs with using pumps. So these are the important parts of this wet box. Another little part that should be mentioned, you don't see in this picture, but it's behind the main equilibrator, is a secondary equilibrator, which works pretty much the same way as the primary one. But we found out during the test a while back, I guess, during a comparison exercise, that we are losing a little bit of gas in the equilibrator just by entrainment with the water. And this gas needs to be replaced. If not, it would create a vacuum in the equilibrator. And so that introduces a perturbation in the equilibrator. So what we do is we connect this equilibrator to a secondary one where we have pre-equilibrated gas in there, and that's what replaces whatever is lost in the main equilibrator. And we monitor this exchange, this entrainment of gas by measuring how much gas goes in or out of the secondary equilibrator by a little vent flow meter. It's in the back of the blue filter, pretty much, but it measures basically this gas exchange there. And you will see later that it's a very important troubleshooting tool for this system, because it tells you what's happening inside the equilibrator. All right. So that's about it. Of course, we measure, I should say there's a pressure transducer on that shelf and a thermometer. So we measure the pressure and the temperature at the point of equilibration, because this is very important parameters for us to be able to calculate the CO2 concentration in the water. All right, so the next slide, please. Oh, okay, yes. Sorry, I think you need to click one more time. No, I'm sorry. Could you go back one slide? Okay, I'm missing some drawings. Anyway, I was pinpointing the diagram. I was drawing the path of the water and the path of the gas through the system, but it's not very important. The water comes at the bottom of the wet box here on the left side, goes through the blue filter and then go through the equilibrator. So we filter the seawater, but then it just goes through the equilibrator and out of there. And that's all the water does. Yes, the cursor does the purpose. And then we take the headspace gas of the equilibrator, we have it go through the chiller on top, then the Nafion tubes, and then it goes through the analyzer in the dry box, and then is recirculated back into the equilibrator. Whereas the atmospheric and the standard gases are not put back in the equilibrator. Obviously, they're vented out. So there's a three-way solenoid somewhere in the dry box that switches and vents the ATM or the standards out directly. Whereas the headspace gas of the equilibrator is a closed loop pretty much and circulates constantly. So it's that gas is always equilibrated at the seawater. And all we're doing is if the seawater changes CO2, then that gas only has to go from what it was before to the new value, which is usually small increments of changes, which allows the equilibration to happen very fast. So this is an important factor. All right, so this is what the system looks like. If you, I'm going to show you the normal operation of the system and what to expect really on normal operation. So I call that, I think Monday and Tuesday operation before whatever breaks down on Wednesday. So next slide, please. When you start the program, you can either let it go and the system will run automatically. But if you need to change some settings, which often you do, you will need to click down on this countdown window that pop-up that will appear. So yes, you click on View Initialization Screen, and then you will get into the test panels and setup screens that are often needed. So that's an important task to do. So next slide, please. The next slide. Okay, this is going to be a bunch of next time again. One more. All right. So this is these initialization panels that show up when you click that countdown window. And first, the system initialize. So you have a series of green LEDs that will light up in series. And when they are all lit up, it says ready. That's when you can start doing things to the system. And the next thing you do, so next. This is, by the way, the test panel. There's other panels. I will not talk about all of them today, but mostly the test panel is the one that you want to access. Here, it's got an area where you will be able to read the different sensors in the system. This is grayed out right now, but when the system is ready, you will get values, and you'll check that the values look okay. This is where this is done. You can also do that on the main panel when the system is running, and I'll talk about that a little bit later. So next. Okay, this area here is a bunch of toggle switches you can activate, so it controls the relay module. So it activates pumps and valves and so forth. So you can also here make sure that everything communicates and is working properly. Next. And then you have, these two areas. So this is where you can test communication with a bunch of things. So the equilibrium temperature sensor, you can see if you're reading GPS and other things. The temperature of the condenser as well is very important. You can check that here. So and then next, right. And the last thing, which is very important, is here in this section, you set the flows of the standards, ATM, or equilibrated gas. So this section is pretty important before cruise. This is what you would get and make sure that everything is good. Normally, once you set the standard gases, they're fairly stable. I've seen a comment of a technician who said it was varying all the time and stuff. This is very rare. Normally, you set them once and they're good. So you click on the standard, then you want to set up, you say set flow, and you adjust the flows with different ways and so forth. So this is the original setup before cruise. It will good. And once you've seen that everything is okay, you click start running, and then the program will run. So next slide, please. Oh, okay. Maybe click next. Okay. Yeah, when the water is running, somebody had asked, what is the good spray pattern that you want to see? We do have a water flow meter, but it's really qualitative. It doesn't really, what's important for the equilibration process is the shape of the spray pattern in the equilibrator. So you have this little spray nozzle on top that's supposed to create an umbrella shape um, spray there. And if you don't have enough pressure or enough flow, then the spray is not good. The intention here, of course, is to increase the surface area of contact between the air and the water so that equilibration can happen as fast as possible. So I don't know if this is a little movie normally. So I don't, let's try to click next, see if it plays. No, it's not gonna play. Okay. I don't know if you can see the shape of the one on the left. It's not dripping, but almost. It's pretty vertical. It does not hit the walls of the equilibrator, and that's really not enough. This is not a good shape. The one on the right is better, even though it's not ideal either. The spray nozzles are all different, so this one is not excellent, but sufficient. So it creates an umbrella. There you can see the seawater forming of films, at some point. So this is what you want to see. There's a little bit too much turbulence, and you want try to avoid this because too much turbulence in the equilibrator, then you might entrain some water with the gas, and then it will wet the system. And this is something you want to avoid. But basically, this is the important part of the seawater flow: is you want to see a nice umbrella and not too much turbulence in the equilibrator. And if you see this, then you're good. Right? Okay. So next. As far as the program is concerned, when the system is running, this is what you will see normally: a plot of the data. Normally, it plots the CO2 concentration, and but you have buttons on top right. Excuse me. Where you can select what you want plotted on this. So you can play around with it. You cannot mess up the data by playing around with that interface. On a daily basis, normally when you want to look at this graph and make sure that the values are reasonable, basically. So anything between, let's say, 100 to let's say 800, unless you're in some weird areas, coastal, it could be higher, but open ocean, so far, this is around 400 and something like this is reasonable values. Of course, temperatures, you should know what these are reasonable. You have, again, on the right side here, the readout of the different sensors in the system. So you can have a quick look and make sure that everything has reasonable values. You have pressure, you have water flow, gas flow, and then these things that we call, there's three values normally that are around 10, and these are important. These are moisture detectors in the system. We do not want water to get into the system past the equilibrator, and these things will tell you if it detects water where it's not supposed to be. We have two, yes, in the chiller or condenser, because so the condenser condenses the water out of it and is drained out at the bottom of the condenser. After this, we don't want any liquid water pass. So these moisture sensors will detect liquid water at these locations. So if those values go down, this is a bad thing. And I will show you that the system can shut off if those values goes down below a certain point. And what we call drip one, the second before last sensor. This is a moisture sensor at the bottom of the wet box to detect any leak in the system. This is good for a cargo ship where the system is not attended. In the case of NOAA vessels or normally there's people around, so we don't shut down the system for this. There's people around that notice a leak, they can shut off the water pretty quickly. So we don't usually do this. But if there's a fault in the system, then that green square I circled on top of the graph there will become red and say emergency stop. And so the system will shut off. And then we have to go in and figure out why it shut off. I'll talk about it briefly a little bit later. And so this is the graph display. You also have possibility of looking at the data acquired. And so this is the little tab on top left here. It says table. You can click on this and have a look at the data. So the next slide actually will show you, if we can go to the next slide, We'll show you what it looks like. There we go. So if you click on the table, then you have a display of all the data, and you can scroll up and down and look at the different columns and stuff like this. So this is something typical I do to see if the system is good. Is first to look at the standard measurements, for example. So you have a column that says what the standards should be and what their measurements are. So this is almost, you say, standard value. I don't know if it's 3, 6, 7, 8 columns, something like this. Yeah, exactly, right here. These are the values of what the standard should be. And then 2 columns to the right of that, you see what has been measured. And those should be pretty close. If if they're more than 2 or 3 ppm, then there might be an issue with the system. So that's something, a quick look to see that the analyzer is working well, that the gas flow is good, and so forth. There's other things you can look at quickly also. So next slide will represent, I scroll to the right of that table, then you can look at the Lycor flow, for example. This is the gas flow through the analyzer, and you make sure that these values are reasonable also, not too high, not too low. You have what I mentioned before, these moisture sensors. You want to make sure that these values are around 9 something. If one goes low, that means there's water somewhere. You have to look at it. The last column I highlighted here is the condenser temperature, which is the chiller temperature. And this, you want to make sure that's at the set point, which is usually around 5 degrees Celsius. If it starts going up, that means the chiller has an issue and usually needs to be replaced. It happens less and less, and that's a big chore to do, but this has to be monitored. So there you go. So that's a quick look at the data to make sure that the system is operational and working well. So next slide, please. All right, so I summarized this quickly, normal operation, making sure that everything is good. So at the time of setup, before cruise, you make sure visual that the system is clean. There's no water where it shouldn't be. Everything is connected. You start the program, you go into these test panels, you make sure that everything communicates, you check the gas flows, that the chiller is starting to cool, and that should be good enough. Then you start the software, and at sea, you do a quick check, of the water flow, that the spray looks good. You can do a quick check of the data, like I showed right now, making sure that you're reading GPS, for example. Standards are good, and so forth. And yes, and then the regular maintenance of the system. So I remember somebody a comment saying it was pretty involved and stuff like this. Normally, if the system works well, which happens most of the time, right, there's fairly little to do. We do a regular freshwater flush that helps a lot to keep the system clean, kill everything that should be not be growing in the system. We clean the blue filter that I showed there, which is the seawater filter. It could get loaded, so we clean that, but that's fairly easy. Unscrew it, rinse it out, and put it back on. The next item that requires attention is changing the chemicals. So I did not mention this, but the some analyzers have a reference channel that we scrub the CO2 underwater out of this channel, and so we use chemicals, soda lime and magnesium perchlorate. They're in a tube, and these get wet over time, and so they need to be changed. But I would say if there's no leak, they could last 6 months to a year. If there's a tiny leak, then they might need more frequent changing. But it's not a hard chore. It's done fairly easy. We have videos about the procedures, so that's not too bad. For longer stops of operation, if you close the standards just in case to avoid leaks and so forth, but that's fairly easy. Sometimes replace some parts, so aquadisc filters, Nafion tubes, they need to be changed. I would say the Nafion probably on a yearly basis. But okay, I don't know if I should answer that. I've seen the moisture detectors. This is our voltage applied to these moisture detectors pretty much. And their principle is that if water, liquid water gets to them, it short circuit the detector, and so the voltage goes to 0. Yeah, so it's so the unit is voltage pretty much. That's what it is. Sure. All right. So regular maintenance, clean the equilibrator. That's a bigger chore. It's nice to do depending on the waters you're in. this does not need to be done super frequently, but it's good to do whenever possible. And then occasionally replace some broken parts and send the sensors back for calibration. So it's not excessively high maintenance, although it could be sometimes. But normally it's fairly easy if everything is monitored well and change in time pretty much. So I will go to the next slide. All right, sorry, this is a duplicate of the a little bit of the previous slide. So I've talked about the regular maintenance. There was a question about what makes a good installation and a good system. So I'll tell you my experience. Normally, the placement of the system is very important. Normally, we put these systems on cargo ships in engine rooms where it's hot and stuff, and those don't do well. Electronics don't do well in hot places. So I would say temperature control space is a great factor for a good system that works well. And then being regularly checked and maintained also goes a long way into the data quality that we can obtain from these things. On ships, getting clean seawater is obviously something important. However, it's very hard to monitor this. So we have procedures to clean seawater, scientific seawater lines on board ships, but I'm not sure these are done, on a regular basis too. So that's something we would like to have a better handle on, is make sure that the seawater lines are clean. And on some ships, like I'm doing an install on the Healy right now, I was told that the seawater takes about 16 minutes to go from the intake to the system. And that's a little bit excessive. So we want to try to avoid too much warming or cooling, depending on installation, from the intake to the system. So roughly, maximum half a degree Celsius is good. So we have to watch this thing. And something I will talk a bit also is for the system to be remotely accessible. Normally on NOAA ships or UNOs, this is not a problem. We have good internet connections, especially now with the star, if I forgot the system, but whatever. We have very good internet connection at sea now, so this is great. So the scientists can log in the system, make sure everything goes good, and we can get daily data transfers, so we can troubleshoot the systems as soon as they break down, pretty much. So that's a great data savers, and so we're really working hard to make sure that this can be done on all installation. All right, next slide, please. So quickly, so I'm talking about the data transfer. So if we have full internet connectivity, we can have remote control through applications like TeamViewer or Chrome Remote Desktop, which is great. If we have limited internet connectivity, then hopefully we can run scripts to at least FTP the data to shore and automate some QC plot, we call them. We quickly check the parameters and make sure that nothing funky is happening. That's a great help also, if we can have that. So this is how we would do it on a good installation. All right. Next slide, please. So now we're going to go into problems that could occur on Wednesdays. There we go. Okay. So I will. It's hard to organize this, but I'm going to try to organize it on what you could see on the system. One of the things when you check the equilibrator and the water flow and stuff, normally because the way it's built, so the water goes down. I've noticed the path of the water. There's an inverted cup inside there, so the water has to go down, back up, and through the middle tube here. And so technically, the water level should be very constant in the equilibrator. And any change of that water level is an indication that something is not right. And normally, of course, so if you entrain too much air, for example, it will create a vacuum inside the headspace, and then the water level will rise. And you should be able to see that in the equilibrator pressure readout, and the water level, of course, also. So, if you see a change in that, then you have to basically you troubleshoot it. The main cause of this is if the pressure changes inside the chamber is because it's not open to the outside. Normally that headspace is open to the atmosphere pretty much through the secondary equilibrator and then the vent flow, or through the siphon break, which I've represented here. So if the siphon breaks, clogs, for example, for whatever reason, this is what would happen. The pressure would diminish inside, the water level would rise and stuff. So cleaning up those siphon breaks would be a good thing to do. If that's not the case, then we would have to look at the air connection between the secondary and the primary equilibrator or the vent flow. We could get clogged or have water in it and stuff like this. So check for blockage basically between the equilibrators. This is the troubleshooting. All right, next slide, please. Another thing that could happen is what I talked about, the emergency stop. So emergency stop is really a programmatic thing. So one of the tabs I did not show before in the initialization screen is the it's called the sleep-wake condition. The system can be set up to shut off at some ports. If you always visit the same ports, then we can enter them in the program, and the system would stop before you enter the port to avoid dirty water getting in your system. That's very convenient. But there's another section also where you can set shutdown conditions for the system. And typically, these are the moisture detectors going below a certain value. So we have the ATM condenser detector, the EQU detector, and sometimes we put the drip one, which is the bottom of the wet box. In this case, it's not. But so we put a limit, limit value on these the voltage, and if the voltage drops below those values, the system will shut down. So if you see an emergency stop, this is where to look, what the conditions are, and if the conditions occurred. If those conditions occurs, then you have to take care of it. Of course, there's a leak in the wet box. It would be pretty obvious. We have to fix the leak. Water at the exit of the condenser, the chiller. Normally, you have to clear the water out of here and see why it condensed too much there. Normally, it's just a matter of evacuating the water a little bit faster. But that I can talk about it some more. But there's ways of fixing that issue. But this is where to look if you have an emergency stop. Next slide, please. The hardest things to select if you have gas flow through the equilibrator gas flow through the analyzer that's slow or very variable. It should not be normally. So the system is able to control the pump speed, the equilibrator pump speed, to maintain that gas flow within limits that are set in the program. But sometimes it cannot do this for various reasons. So I represented on the right side here the circuit of the gas, this headspace gas, through the system. So it first goes through the chiller. Yeah, we start on the right there. It goes through the chiller. It goes through the equilibrator pump. Then through this little aquadisc filter, which should stop any liquid water. Then goes through the Nafion tubing. And then the green part is the analyzer, and the little orange ball is the that three-way solenoid that I talked about that vents the gases, the ATM or standards. They're vented out instead of being returned to the equilibrator. And this, anyway, this could create problems if you get stuck. So if we click on next, I think the first problem. Normally, the chiller is not a problem unless there's water coming out and the moisture is detected, but we've talked about this already. So the issue, the problem for low gas flow could be the pump. And so, actually, yes, if you click next again, sorry, my animation is not going. So there's several reasons why the pump could be an issue. It's either not working, which would be obvious, it needs to be replaced, or it could be dirty. So these little pumps are diaphragm pumps, and they have little flaps inside. And sometimes, dirt gets in there, and so the flaps are not able to close properly, and so the pump really doesn't function well. That's usually the symptom of this would be a very variable flow in there. And so the way to clean this is, if you could click next again one more time, it'll be either you can run water to that pump. If you disconnect both ends and run hot water, this sometimes is the easy way to clean it. If that doesn't do it, then the next step would be to open the the head and clean the diaphragm itself and those little flaps and then close it back up. It's a little bit of a chore, but it's feasible. But this is the way to do it. The next step of the problem, so if you click next again, there it goes, the Acrodis filter. So that's pretty obvious. Again, click next. And then one more time, there we go. Okay, so that means if the Acrodis filters are the issue, that means they're wet. They have water in it, and then so those can be dried and reused fairly easily. So that's not a big chore at all, and that's fairly easy to do. The next step, so click next again, would be the Nafion tubes, right? And those are, so the membrane is very water sensitive inside these Nafion tubes. If there's liquid water in these tubes, the membrane will expand and twist, and then it will stop the flow of the water. So these, we have to replace them. There's no drying them or reusing them. So, but you have to be aware that, yes, they could block the flow completely if they expand and create problems. Okay, next. Okay, and this is something, yes, the return line in the equilibrator could sometimes get clogged with salt. There's a salt buildup that happens in this line that's kind of hard to see, but if you know that it could happen, then it's visible. So if you click next again, so yeah, salt block in the return line, what you have to do is pull out that line out of the equilibrator. It's a pass-through, so it's fairly easy to do, and scrape it off or unblock it with water or something like this, and then everything is good. So it's not hard maintenance either, but you have to be aware that this could happen. All right, and that's all the. Oh, sorry, no, there's one more. Obviously, sorry. So click next again. There you go. Yes. So the reason why you could not have a low gas flow is because you have a leak in the system, and then there's then you have to find the leak, unfortunately, and so that could be a little bit time consuming. But this is the last reason why you could have low flow. All right. Next problem for Wednesday is also when you look at the different sensors. So the vent flow value is something you want to look at fairly easily because it tells you a lot about what the system happens. The path of the gas got messed up in the presentation. I did not notice that. I'm sorry, but basically the black circle there is the same as before. It's a loop, and so if anything happens in that loop, then it will show up in the vent flow normally. That vent flow is normally could be -10 to +20, 30. That's the regular value. It's fairly low. If it's anything higher than this, then there's an issue, and it could be either positive or negative. If it's positive, and I indicated the sign of the vent flow being positive, that means air is going inside the secondary equilibrator. That means you're losing air somewhere in the primary equilibrator. And if it's negative, that means you have too much air in the equilibrator and it's being pushed out of it through the secondary, out of the vent flow. And so for these problems, the three-way solenoid that I talked about before, being stuck in one position, usually the return to equilibrator position is a reason why this could happen. And all the standards or ATM gases are being returned to the equilibrator and they are pushed out and then positive. But other than that, it's a leak somewhere in that loop that creates that problem. So the pump either pulls out the gas from the equilibrator and never returns it to it because it's vented out somewhere, and so you would have a high positive flow, or pushes, there's a leak somewhere else and it pushes too much air inside and then it becomes negative. So that this is a little bit tricky to diagnose, let's say, but this high vent flow reading an indication that there might be a leak somewhere in the system. So it's very very important to monitor this one. All right, next slide. All right, and then outside of all this, the water and the gas flow, then you have electronic issues. I know somebody said that they had a lot of issues with COM ports and stuff like this. So this is also an issue that I have not seen in a while. The COM ports being reassigned and then the system not communicating and stuff. This right now, the system is working pretty well with this. So the main setup, so you have the computer of the system is connected to an Ethernet hub, which is also connected to two Ethernet to serial devices. So they all set up with IP addresses, right? And that's fairly stable. I've not seen the serial numbers, being mixed up or changing much. So that's fairly stable. If you have like all of a sudden all the system sensors are not communicating, but I would look into that. And sometimes it happens, somebody touched the computer, changed the IP address for some reason, and then everything stops communicating. But that's very rare if you monitor the system. But that's something to check. Ethernet cable being badly connected, that's a good reason. IP address changing. I would look into that setup breakdown here. That's what happened. If you only have one of the system sensors not communicating, then this is not the place where it breaks down, I guess. So I would look at the sensor itself and make sure that the sensor is working. You also have connections to auxiliary sensors like Seabird 45 or 38. And if these are not being read, I would check the sensors or its own connection to the system. But normally the system should be okay. We have rarely problems in this department. All right, next slide, please. Okay. There was a question by somebody said, okay, how can we improve the CO2 measurements or augmenting them really? And so right now we are trying to do this actually. There's different ways. Not most of our system, a lot of our system have, for example, oxygen sensors on it. The one that we like is the Endera. It's very easy to integrate to the system. We have a flow cell for it. But I don't see why we could not integrate a Seabird 63, for example. That should be fine as well. So oxygen measurements are nice to go along with our CO2 measurements because it informs us about the biology of the waters. And so we can do some inference about this. We can measure nutrients. There's a Stuna instrument that measures nutrients. This is mostly for productive waters. Some other waters, open ocean, you rarely see a signal for this. So it's mildly interesting. We can complement our measurements with other carbonated system parameters. So pCO2 is one, but we also have pH, which is a fairly easy measurement to do on ships. And now we have this new system. It's underway, a total alkalinity system built by Kongsberg, and it's on a couple ships. It requires quite a bit of maintenance, so we're not, we have not put that on ships yet. But that's something we could do also if you have inclination. With these two parameters, we can calculate and define the whole carbon system. So that's very interesting. Something else we're trying to expand is measuring other gases than CO2, and N2O and methane are examples of it, for example. But that's a starting effort right now. So yes, this is the end of my presentation. I really wanted to say a big thank you to all you guys, marine techs. Without whom we could not get the good data. So really a big thank you. I never say enough about this, but here you are. Thank you so much. And if you have any questions, I'll take